Okay, so in the last video, we were talking about this idea that as your imaginary sample sizes become larger and you do those sample distributions composed of a larger and larger number of sample means, the mean of the sample means is going to more and more closely approximate the population mean as your sample size becomes larger. So that is all based on the idea that is illustrated here on the slide, referred to as the central limit theorem. So I want to just explain what's on this slide. So we've got four sort of data sets here, and you'll see this normal curve. That means the shape of a normal curve is just sort of put on all of these as a backdrop so that you can visualize what a normal curve would look like. So let's say you collected, some data, and what you have here is you've done binning. So let's say this represents maybe 0 to 10, 10 to 20, 20 to 30. Okay, so you have these pretty wide score ranges. Okay, that's what this means, few rows. That means that you're doing this sort of large amount of binning here. Instead of individual numbers, you're saying everything from 0 to 10 is represented in this bar on the bar graph. Okay, then this phrase up here, few trials, means that you've only taken a few samples. Okay, so not only are your scores not that discriminating because your bins are wide here, but you've only taken a few samples and graphed the sample means. Okay, and basically you can see you don't end up with a very good normal curve here. I mean, here, it's not great, right? It's mediocre. All right. In the next one, you still only have your 5 rows, okay? So you're still using these wide ranges for your data, few rows, but this time you've done many trials. You've taken lots and lots and lots of samples and graphed those, and look at how much more closely it resembles the normal curve than this one over here when you took very few samples. Okay, now down here, you have, instead of having these wide scored ranges like you have up here, you've narrowed your bin size. So maybe this only represents like 1 to 3 and 3 to 6, 6 to 9, and so on. Okay, so that's an improvement, but you still, as you see here, have only taken a few samples and done a few sample means, and you can see, you can sort of roughly see the normal curve there, but it's not great. Now, in contrast, look at this one. You've narrowed your score ranges, and you've taken lots and lots and lots of samples and started graphing your sample means. And this illustrates the idea that a higher number of samples is going to give you a curve of sample means that's much closer to the normal curve. And if you read about the central limit theorem, one thing you're going to see is this number 30. This number 30 keeps showing up. See it down here on the slide. Okay, because basically, as we saw outlined in Statistics Without Tears, if you have a very well randomized sample of at least 30, you can do all these statistical calculations by starting with a very important assumption, and that assumption is that your sample mean is going to approximate your population mean. You don't really know your population mean, but if you have a good randomized sample of over 30, that is the assumption that you go on, that you start your calculations with. Okay, and this is in a footnote on page 94 of Statistics Without Tears. It's just a footnote, but it's very, very, very important. That even though we don't know for sure what our population mean is, we infer that our population mean is our sample mean, again, assuming that our sample is well randomized and at least 30 or more. And this is important because remember, we have to go back to the reality of the fact that we usually only have one sample, right? Remember when we were looking at all those other graphs, we were imagining that we were taking almost an unlimited number of samples, right? But in real life and scientific research, the truth is we only have one sample. And so we want to be able to make a statement about our population mean based just on our one lone sample. So Statistics Without Tears has a very good explanation of the factors that can affect this important calculation of standard error of the mean. And this is from page 92. So the standard error of the mean, whatever that is going to be affected by three main factors that the book points out. Number one, the standard deviation of your one sample. Number two, the size of your one sample. And number three, the proportion of the population covered by your sample. Okay, so let's start here with factor number one. Your standard error of the mean is going to be affected by the standard deviation of your sample, which makes sense since the standard deviation of your sample is right there in the equation for standard error of the means. And as you see here, the larger your sample standard deviation, the larger your standard error of the mean is going to be, right? Even though standard error of the mean, remember, is always going to be smaller than the standard deviation of the sample, right? And I wanted to say it really just makes sense here. The first one just makes sense because the more variation in the values of your sample, i.e. the more spread out it is, the larger the standard deviation is, obviously the more likely that means of samples taken from that data are going to veer further from the population mean. Okay, next one, number two. Standard error of the mean is going to depend on the size of your sample. Again, number one, it makes sense it's going to depend on that because it is right there in the equation. But as opposed to standard deviation, standard error of the mean, sort of, bigger means bigger, okay? Sample size actually has an inverse relationship to standard error. So the more values represented in your sample, the larger sample that you take, and again, remember, that means the larger all of those imaginary samples that make up your sample mean distribution that you have in the back of your mind. So the larger your sample, the less likely that outliers are going to pull your sample means away from the actual population mean. So the means are going to cluster closer and closer to the population mean. So larger sample size here, right, means a smaller standard error of the mean. So, bigger sample is better. Okay, and then the last factor that affects standard error of the mean is the proportion of the population that is covered by your sample. Now, this can affect the standard error, right? I.e., the larger the proportion covered by your sample, the lower your standard error is going to be. Okay, that's sort of the general truism. So if you know your entire population is 500, and you had to choose between doing a sample of 10 and doing a sample of 100, obviously the larger proportion sample, the sample of 100, that's going to give you a lower standard error. That just makes sense, right? But compared to the other factor, as you see here on the slide, this is going to be the least important factor. Why? Well, Statistics Without Tears explains it pretty well, because any real reductions of error come into play when your sampling fraction exceeds 10% of the population, which is actually very, very high. And so very few samples are ever going to come close to being 10% of your population of interest. Okay, and even then, the error isn't even reduced that much. Even if your proportion exceeds 10%. So definitely the least important factor. So let's try and use the example right in statistics without tears. Okay, remember, we had there one random sample of 100 students' exam scores. And we are told, we're given the information that there is a mean score of 50 out of 100. Okay, we're also told that the standard deviation is 50 points. So mean of 50 with a standard deviation of 15 points. So filling those numbers in over here in our equation to our standard error of the mean formula, we get that the standard error of the mean is, okay, we need the standard deviation, that's 15. Okay, so that's 15 divided by the square root of the sample size. So the square root of 100, that's 15 over 10 or 1.5 points. So our standard error with that data set is 1.5 points. Now, what can the data on this one sample of 100 students tell us about our population mean? Well, remember what we talked about before, that if we had taken sort of an imaginary infinite number of samples and plotted the means, that curve would be normal. Okay, and what that means is we can use our 68, 95, 99 rule. Okay, and because we took a large, well-randomized sample, our sample here is well over 30, right? We've got 100. So when we do that and we use it to calculate the standard error of the mean, then when we take our standard error, we can come up with our confidence intervals, right? So we can validly now make the statement that the probability of our true population mean, if there were, say, 50,000 students that had taken that exam, and we just took that one sample of 100 students that had a mean score of 50, with our standard error of the mean being 1.5, because we calculated that, we can make predictions about what the true population mean, say, of all of those 50,000 students that took the test. We can say the probability of the true population mean falling within one standard error of the mean of the sample mean is 68%. Or, as you see down here, we are 68% confident that the mean population score for all students that were tested is going to be 50 plus or minus one standard error, right? Plus or minus 1.5. So our 68% confidence interval is 50 plus or minus 1.5, or 48.5 to 51.5 points. So that's your 68% confidence interval. Now, on the other hand, 68% confidence interval, that's pretty good, but we probably want to be able to report, in fact, a higher confidence interval than 68%, right? Because a 32% chance that our population mean falls outside our interval is probably not going to make our data very meaningful to anyone. So let's see what happens if we go out 2 standard errors of the mean beyond the sample mean. Okay, if we do that, okay, the probability of the true population mean falling within 2 standard errors of the sample mean, that goes way up to 95%. Or if you want to put it in terms of confidence interval, we are 95% confident that the population mean lies between the sample mean and plus or minus 2 standard errors. So that's a pretty easy calculation, right? Remember, we're still using our same 1.5 standard error of the mean, and we need to take that times 2, right? Because we're going up and down 2 standard errors. So 2 times 1.5, you see down here, is 3. So we have our 95% confidence interval that our mean population score for all students tested is 50 plus or minus, and then we need 2 standard errors, so 50 plus or minus 3 points, or 47 to 53 points. Now that's getting a lot more meaningful. We can say we're 95% confident that, you know, our population mean student score is between 47 and 53 points out of 100. Here is our familiar normal curve showing our confidence intervals. Okay, 68% is going to be sample mean plus or minus 1 standard error. To get a 95% confidence error, it's going to be sample mean plus or minus 2 standard errors. 99% confidence interval, sample mean plus or minus 2.5 standard errors. And then if we go all the way up to 3 standard errors, remember we get that 99.7 confidence interval, which is shown in this left-hand diagram there. Okay, that's the end of this video lecture.